So let's start with our second talk, and we have Michael Ruffi here from Radboud University, right?
It's UCLA.
Oh, sorry. Okay. I'm from UCLA. I'm very sorry. So classical observables from quantum scattering amplitudes. The floor is yours.
Okay. So let me start by thanking the organizers for having me here. It's very nice to be in this somewhat different setting. And I come from a bit of a different background, so if there's questions, of course, we should discuss later. This is meant to be very superficial in some sense. All right, so the topic of this talk is going to be classical observables from quantum scattering amplitudes, and it's based on work I've been doing during the past few years together with a host of different collaborators. Now, I have to start by maybe a quick disclaimer. There are not going to be any results on quantum scattering amplitudes or genuinely quantum results in this talk. The topic of this talk is going to be more that a quantum viewpoint can be extremely healthy for doing classical computations. So let's jump right in. The motivation for this line of work is gravitational wave physics. Of course, one of the most interesting things we have learned in the last 10 years are that gravitational waves are a real phenomena in nature. And they come basically from all different kinds of physical objects that you can think of. For example, recently we learned that there's also a gravitational wave background in the universe. And there are many systems that you can look at, and the most interesting historically have been gravitational binary systems, and these are going to be the main topic of this talk. And the physics goal of this line of research are also pretty rich. For example, you can do this to use this to do strong field tests. You can make you can do cataloging of black holes. You can do tests of the neutron star equation of states and so on. So right now, this is done by ground-based observatories, namely the LIGO, Virgo, and the CACRA collaboration. There have been around 100 events that have been observed so far, and just recently the fourth run has started for these observatories, and they promise that they will give us about 200 more events in the next few years. These experiments are actually very impressive. They are very precise. They measure these things to about 1,000 cycles or more. The length changes are also pretty mind-boggling, and we have very good control over the experimental errors in this setup. What this line of research that I'm working on is actually targeted more is the next generation of experiments, which we will see around 2035. These will have order 10 to 100, a factor 10 to 100 improvements in signal-to-noise ratio. And in particular, this will also involve a far bigger reach and greater sensitivity, and therefore more data. And we will also be able to see extreme corners in phase space, in particular with the space-based missions such as LISA around 2035. In principle, all of this can be done numerically. In the past 15 years, people have understood quite well how to do numerical relativity. The problem with this is that it's still relatively costly. A typical numerical relativity template can take up to 10 to the 5 CPU hours, typically for the first observation. And we need lots of these templates because it's done by some interference measurements. For example, for the first detection, 250,000 templates were needed, and this basically means this is far too much to do with numerical relativity. It becomes even harder if you go to certain corners in phase space. A particular example is this large mass ratio limit, which will be important for LISA. Here we will see like a factor of a hierarchy of 1,000 to 10,000 in between the masses, and this is just very challenging for numerical relativity to do. The solution to the problem is that one uses partially analytic information, for example, post-Newtonian physics, which is a fully analytic approach, or the so-called effective one-body approach, which uses partly numerical relativity information. And in all of these, key input is, for example, the perturbative correction to the Newton potential. Now, in this talk, we're not going to focus on the in-spiral problem, where two black holes coalesce, but we are instead going to focus on the scattering event. This might be a little weird to look at because, for example, if you look at the signatures of these types of events, in-spiral event has a very characteristic signature, which is easy to detect in a detector or filter out from the background, whereas the scattering event looks rather boring, so it's very hard to detect. And we are also not really, it's unclear how the event rates would be for such events. So it's very hard to make any predictions whether we will be able to actually detect these things in the future. So the reason why we're looking at this is more to get some better understanding of how these things look like. And in particular, scattering is arguably one of the simplest processes you can look at in any quantum field theory. And it's very beneficial to look at both for numerical and analytical approaches. It's also a problem that can be treated fully in a perturbative setup, so we don't have a merger, which might sound boring, but it's also very nice to keep the problem clean. And there's a very close relation in between the bound and the unbound problem. Sometimes people think about this by some kind of analytic continuation. All right, and for us, the one important point is that it meshes very naturally with a scattering amplitudes program. All right. Also, just to say that this doesn't really happen in vacuum. Also, people in classical GR are very interested in the problem. We also heard earlier from Knorr that also people in this community are interested in scattering, which is also very encouraging for us. I can maybe highlight really quick that we had a recent study of this, and we were comparing with what's called gravitational safe force, where you take the limit of one mass being much larger than the other. And what we were able to do is we could find, with this semi-analytic approach, we could find that the approaches are very complementary and that one approach can help the other. And by combining them or by comparing them, we find that we can actually do this perturbative computations to a very high order, up to the percent level or even better. Because this is an observable-based session, I can maybe highlight a few observables that we are concerned with. The basic one is, of course, the waveform, which looks like this. Another one is the scattering angle, which is personally our favorite observable to look at. We have radiative losses. If spin is involved, we have the so-called spin kick. So the particles will change the orientation of the angular momentum during the process. We can look at the time delay, and we also have things which are maybe a bit more academic because we don't have like a full angular resolution of the problem, but we could also look at things which are so-called event shapes. Now, the problem can be treated with perturbation theory. If the particles are separated very widely, there's a natural expansion in a weak field. We can just solve Einstein's equation perturbatively. This was already featured in JJ's talk earlier. If you try to do this, so this naturally leads to Feynman diagrams or to a Feynman type diagram computation. But the problem with this is that it introduces, depending on the gauge, it introduces very complicated Feynman rules. And this very quickly grows out of hand. If you just do like order of back of the envelope computations, you see that at some point, maybe not at the present order, but at some point this will be very intractable with Feynman diagrams. And this problem is, of course, very familiar in other corners of physics as well. The problem, the solution around this is by adopting an on-shell perspective on the problem, focusing on scattering amplitude. Maybe just to highlight this very typical example that we like to give. If you're trying to compute some scattering amplitudes for gluon, For example, 2-gluon goes to 4-gluon, which is something that at some point was a state-of-the-art computation. You'll find that this computation leads to a result which is basically 15 pages long. But if you take an on-shell standpoint and you compute the on-shell amplitude, you will find that in the right variables it only collapses to a single line. So this really tells you that the objects of interest might be much simpler than what you have in intermediate expressions. In general, the objects we're looking at are also highly constrained by symmetry and so on, which will be important to do these computations. Now, how can we leverage this to make a classical computation? People have figured this out quite a long time ago. Of course, if you can compute the quantum S matrix, you should have all the information about the classical S matrix as well. Basically, this work was the first work where this has been done in 71. And people have been using this at the time to compute the first subleading corrections to Newton's potential. This is a very nice idea, but at the time, people didn't have the tools to really push this to very high orders. So it didn't really gain any traction at the time. So there's really only a few papers around that time that study this. And this is the basic point. If you want to convince people, you have to do something new. In the meantime, we've become much better at these computations. And this is also why recently there was an increased interest in revisiting these computations, which was also urged by the gravitational wave community. Briefly, the setup that we're using. Quantum gravity is encoded in, we're just using some low energy effective field theory. And also in principle, we're including finite size effects for the particles. So for example, if you have a neutron star, we can all encode this in higher dimensional operators. But in principle, the process we're considering is scattering of point particles in Einstein gravity. At some point, it's very important to include these operators, but this is just a technical caveat. And this can very easily be extended to include the spin of the particles as well. The classical limit, which we eventually want to take, is dictated by the correspondence principle. We have a very strong hierarchy of scales. Basically, the angular momentum of the system is very large. This is really, if you go to natural units, you will have something like 10 to the 40 orders in this parameter. So the natural expansion is really in small j. The hierarchy of scales can also be phrased as having a small Compton wavelength with respect to the Schwarzschild radius, which in turn should be much smaller than the impact parameter to have perturbative expansion. And we will be interested mostly in the long distance physics, which corresponds to Stroff-graviton exchange. And in principle, the rule is that the graviton exchanges will be of order h bar, but we will consider processes where there is basically a 1 over h bar times of these exchanges, leading to eventually a order 1 result. This was already quickly mentioned. The basic building block for computation are 3-level amplitudes. JJ told us about the double copy, so I won't give you much details. The basic point here is basically we are very efficient at computing these 3-level amplitudes. Now, as I was saying earlier, the amplitudes are very highly constrained by the structure, and this can be leveraged to compute loop-level amplitudes from 3-level amplitudes. And this is done by the method of generalized unitarity, basically constructing an integrand from the residues. And so if we are very good at computing 3-level amplitudes, we are also very good at computing loop-level amplitudes. And this has been shown to be very efficient and in many different contexts. For example, in supergravity up to the 5 loop orders. Once we can compute an integrand, we have to also perform the integration. This is a separate step, as was also mentioned by JJ. We in general have to deal with Feynman diagrams. And the way we deal with them is in a very standard procedure from collider physics, in a 2-step procedure, which first requires integral reduction, and then the evaluation of the remaining integrals that remain after reduction. And this is well understood, and it basically leads to a problem in linear algebra, which we can solve by making use of computers. The remaining integrals satisfy Fuchsian differential equations. This is also a very standard insight from collider physics, and there is a vast literature on how to solve these integrals. The key point is it's basically very important in all the steps that you always have to take the classical limit very, very thoroughly. And in this case, the classical limit leads to a reduction in the number of integrals you have to compute, but it also makes the problem much simpler because the number of variables drastically decreases. So the full problem depends on both the masses and the energy and the impact parameter basically of the scattering, whereas the classical limit only depends on a single variable. And also the resulting functions become much simpler in the result. Just to prove. How much do I have? 5? Okay, cool. Now, once you have the setup for the amplitude computation, the question is, what can you do? Like, if someone hands you an amplitude, how to extract the classical physics from this? And the basic problem here is that amplitudes are themselves not observables. This is something that's very well known, of course, also to people in collider physics. There are IR divergences hiding, and also what is maybe a bit more pressing is that the amplitude as expanded in the classical limit itself doesn't have a well-defined limit. Basically, if you increase the number of loops and you do the power counting properly, you will find that each higher loop order diverges even more strongly with 1 over h bar. And the question then is how to deal with this. There's a bunch of different approaches how to do this. One possibility is to basically do a matching computation to determine the scattering potential, starting from either the Schrödinger equation or the Lippmann-Schwinger equation. And in this approach, you will find that the divergences match. And this has been the first, or for a long time, this has been the most prevalent approach. It's very nice because it's very close to what the analysis actually wants, because the output of this computation is the potential. The small issue with that is that the potential still is not really observable, so it still carries some coordinate dependence, which we don't really like. The maybe more scenic approach, and this is to quote the authors of this approach, is to go directly through observables. Then we basically know that all the divergences should cancel from the observables, and we can take the limit h bar goes to 0 just at the level of the observable. It's basically just something you can go through the steps very, very easily yourself. You just define a difference in an observable in between an asymptotic out and an asymptotic in state, and you can find that you can relate this quite straightforwardly to scattering amplitudes. And this is something that's very, very tractable in practice, and it's very similar to what people would do in collider physics. This has been done to obtain a bunch of new results. So the radiated energy in the process, the radiated angular momentum, waveforms, which is a pretty recent development, and also observable with spins. And exactly, and in principle, it's also very straightforward to get more differential observables. So, for example, like angular distributions and so on out of this kind of framework. There's another way how one can deal with the divergences, which is basically one can resort to unitarity. The divergences should exponentiate, and one finds a phase which contains all the classical physics as well. I don't have time to discuss this here. Eventually, what the aim of this program is to push this to a very high order. The more recent version of this program is very efficient as compared to what people had in the 50s. There were many state-of-the-art results that we've produced with these results. There's like many hundred papers by now in the last few years that have been written on the topic. Spin has been considered at the order g to the 4, and radiative effects have been included as well. The question, or basically what we want to do, is we want to push this computation to even one higher order. This has a multitude of reasons. One of them is, for example, as I was discussing in the overlap with the classical computations, to do better benchmarking or to improve hybrid models, or to relate back to the bound problem. The problem in pushing these computations to higher order is that basically around every corner, we also saw this in JJ's talk, there's exponentials hiding. So you might be deceived by the fact that the 3-loop order is relatively easy with all the improvements that we made to the problem. But the 4-loop problem is very hard, and basically the reason for this is just the number of integrals and so on just explodes. So we need some new ideas to tackle the problem. And what we recently did in order to get some handle on improving and making these computations at the next order is by going to a simpler problem. And what we did is we considered scalar electrodynamics at the 5th order in the fine structure constant. And by this, we basically showed that 4-loop computations are actually possible in the setup. And we are very confident that we can leverage what we learned from quantum electrodynamics to gravity. So there's a lot of overlap in the computations, and we also made more progress since we put out this result, basically. So maybe with that, let me conclude. Maybe the main point of this talk is that scattering is a very interesting process that people should look at. It provides a very clean environment to study, and that should help with clearing up conceptual issues. There are many issues in the classical GR community that are still floating around, and that prevent even from incorporating results into the pipeline for LIGO and Virgo and so on. There are many observables that one can consider. We have constructed classical observables by using a quantum object, a quantum scattering amplitude, and we have used a manifest on-shell setup, which is very helpful because it avoids all the algebraic complexity and the gauge dependence that one would find if one did the computation in a different way. We have many new results, and the program is instrumental in pushing the progress in the field. And maybe the last thing is that we took a lot of information from collider physics in putting together this framework. It would be interesting to see if there's other corners of physics that could teach us something, and I think this might be a place for the community here.
Yeah, thank you for this nice and very elaborative talk and new perspectives. Are there questions? Up there.
Yeah, thank you for the nice overview talk. So 2 things. So when you say millions of integrals, this is the number of master integrals, I guess? Or
no, the number of master integrals is around 4,000. So
okay, 4,000. Okay, that sounds a lot better. And when you said, so you mentioned special functions.
Mm-hmm.
At 3 loops, you get elliptic or integrals that are elliptic.
Yes.
Have you identified what kind of special functions or what kind of geometries
we
there
are
appear?
in the process of doing that.
See, okay.
I mean, we can discuss, but yeah. We can discuss.
Okay.
No, but
yeah.
maybe, yeah.
Okay.
Yeah.
I don't see a further question, but just briefly, can one compare, or do numerical relativity calculations exist of these scattering processes?
Yes.
That you
I think this
to?
was actually on a slide and probably just skipped over it. There's actually also overlap with numerical relativity, and in principle, there's like this picture where we have different frameworks. So one of them would be this, I don't have the plot here, but one of them would be the self-force, which is particularly good in one corner. We have the perturbative approach, which is good in another corner, and then you have the corner of phase space where you really have the non-perturbative physics, where you really need numerical relativity. And people have been, really recently, people have been doing more numerical relativity results, more numerical relativity computation, as for example, this one plot here from Damour and Retegno, where they compare to numerical relativity and also find percent level agreement in between what we are doing and what they are doing. So that's very encouraging as well.
Anyone else with a quick question? Otherwise, let's thank Michael again.